Hi everyone. As a mechatronic designer, you are often responsible for choosing and determining a transmission in an electromechanical drive system. An example is this conveyor belt that is moved forward by means of two pulleys over here. Practical examples similar to this are a scanner, a wafer transport system, conveyor system, or a printhead carriage in a printer. But to determine the motor and the transmission, you must first know the load torque. But how do we do that? And that is what this video is about. So here we focus mainly on drive systems with a load torque that consists of a constant part, which is the Coulomb part of the torque, and a speed dependent part, the viscous part of the load. And because torque can be determined by measurements, we use a PMDC motor as a measuring device. This is because the PMDC motor has a linear relationship between the motor current and the motor torque. So by measuring the motor current, we have a measure of the load torque. After all, the motor torque T is equal to the motor constant or torque constant K times the motor current I. To determine the torque speed characteristic of the load, we also need the angular velocity of the motor, and we're going to measure that by using an encoder attached to the motor shaft. So, summarized, we are going to use a PMDC motor as a measurement tool to determine the load torque by means of measuring the motor current. And we're going to measure the load angular speed by measuring the encoder frequency. And in this way we are going to determine the Coulomb friction of the load, so the constant part, and the viscous friction of the load, so the part of the load that has a linear relationship with the speed of the load, for example due to bearings. Note that the measurements may not take too long, because otherwise the motor will heat up, which will have an impact on the motor constant K, and that will affect the measurements. So an oversized motor for your measurements will be a good choice, or choose a motor with rare earth magnets. And make sure that the motor parameters, especially the motor constant, are well known. So this is my setup for the conveyor belt. Here we have my conveyor belt, which is powered by this voltage source over here. And in this conveyor belt setup we have the motor over here. You can see it very good in this picture, but attached to that motor shaft, this is the encoder. And on the other side of the motor there is a belt, which is also not shown in this picture, which drives that pulley over here. So we are going to measure two things. The motor current, we do it by a current measurement device over here, or you can use an inductive current clamp. And we are going to measure the frequency of the encoder by means of frequency measurement device, or you can use an oscilloscope for that. And we are going to change the speed in several steps by changing the motor voltage, so the voltage towards the motor. And these steps in voltage don't have to be equal values, but we need a couple of measurements in order to get a good measurement result. So at every voltage we measure the current of the motor I, and we measure the encoder frequency over here. So I did that for a couple of voltages which I apply to the motor, so I get a number of current measurement points and a couple of frequency measurement points, so the frequency of the motor shaft. Now we are going to use motor and load data in order to calculate the load torque in every measurement point and the load angular speed in every measurement point. Well, we use a motor over here from Parvex, which is the RS220, and we need from the motor constant or torque constant KT, which is 0.057 Newton meter per amp. We have a motor friction, so the friction of the motor itself, which is 0.012 Newton meter or 1.2 Newton centimeter. And also the motor has some damping, which is equal to 1.3 times 10 to the power minus 5 Newton meter per radian per second, or Newton meter second per radius. We have also an encoder attached to the motor, and the encoder has 500 counts per revolution. So every revolution of my motor shaft yields 500 counts. The load is driven by a transmission belt, and that transmission belt has a transmission ratio, the ROVB, which is equal to 14/24, which is defined as omega load divided by omega motor. So it's a reduction. And the transmission has an efficiency which is equal to 0.9. So now we have the measurement points over here. We have the data of the motor and of the transmission. So for every measurement point we can calculate a couple of things. First of all, we are going to calculate the angular speed of the motor. And we can do that by using in every measurement point the measured encoder frequency. We divide that by the number of pulses per revolution, 500 in this case, and we multiply it by 2 times p. So in that way we get the angular speed of the motor. And based on that we can calculate the angular speed of the load by multiplying omega motor by the transmission ratio ROVB. We can also calculate the motor torque by multiplying the measured current in every measurement point multiplied by the motor constant kT. But this is the motor torque which is caused by the motor itself and caused by the load. So in order to calculate the load torque we need to calculate the effective motor torque. So the motor torque which is not coming from the motor itself but which is caused by the load. So we have to subtract from this value the friction of the motor itself and the damping times the angular speed of the motor. And that net motor torque is equal to the transformed load torque to the motor shaft, so T star load. And by having this we can calculate the load torque by multiplying the transformed motor load torque by the efficiency of the transmission ratio and divided by the transmission ratio, the ROVB. So now we have all our calculated data in every measurement point, and now we can draw the load curve by setting on the horizontal axis omega of the load, so the angular speed of the load, and on the vertical axis we put the load torque. Now we can determine what we want to measure. So we can determine the Coulomb friction torque, which is the intersection point of the load speed characteristic with the vertical axis, and we can determine the viscous friction torque, which is the slope of the curve we have measured. And of course we can do that in Excel. And I have an example put over here in which I worked out some measurements. So I did some measurements over here, measured in a couple of points the motor current and the frequency of the encoder. Based on the frequency I can calculate in every measurement point the angular speed of the motor, and using the transmission data I can calculate the angular speed of the load. By using the current measurement data I can calculate the motor torque, the net motor torque, and based on the transmission information I can calculate the load torque. So now I have for every measurement point the load torque and the angular speed of the load. And I can make a graph of it in Excel. So these are my measurement points, and I could put a trend line in it, and the intersection point of the trend line with the vertical axis is my Coulomb friction torque, which is 0.0096, the constant factor over here in the trend line definition, and the slope of this characteristic is equal to the viscous load. So that is equal to 0.0001 Newton meter per radians per second. So that is all. I hope you enjoyed it, and I hope you really can use this measurement setup. Thank you for watching, and I see you next time.